Well, welcome, folks. I think I have a friend with me. It's Mr. Sams, and I think he has something to share with you.
I have yet another poem. This one is sulfur.
Sulfur. Ooh, sulfur stinks, though, doesn't it?
Sulfur! Sulfur, yellow element, so bright, thou I heatest, thine odor is bad. Like the rotten egg, thou burnest my nostrils. Brimstone thou art, and torment thou dost bring. But wait, lest mine ears deceive me, thou art necessary for life. The curls of mine hair cometh from thy bonds, glorious, yet putrid sulfur.
Sounded just weird. That was poetry?
You didn't like that?
No.
That's an egg?
Yeah.
When do eggs have, like, sunbeams coming out of them?
Well, at first I was going to draw a sun, and then
I guess you could fry it in bacon grease or something, maybe.
Yeah, well, you know.
That's the best way to do it.
There you go. Ooh, yeah, okay. Hey, today...
BLT with an egg fried in the bacon grease. Oh, it's my favorite sandwich in the world.
That sounds very unhealthy, Mr. Sanders.
Oh, yeah.
Okay.
The guy whose dad just had a heart attack and open heart surgery, you think would be eating a little bit.
Yeah, you need to work on that, Mr.
Yeah.
Sanders. Okay, all right. Today we want to start with another problem. We want to solve for Ka. We've always been given Ka, but here's a problem with lactic acid. Lactic acid, speaking of exercise, this is what builds up in your muscles when you exercise and what makes your muscles sore.
You don't exercise, you got stuff building up in your arteries. You do exercise, you got stuff building up in your muscles.
But then it washes out.
Oh, is that how that works?
Yeah, it is. I thought you knew biology.
Well, you know,
okay.
I just like making excuses.
So, hey, in fact, I didn't read this. I saw lactic acid. I told you all about it, and my question actually says it helps you feel fatigue. So now we have a 0.1 molar solution of lactic acid. We're trying to find Ka. So, but we know the percent dissociation. So first of all, let's go ahead and write our reaction. The formula of lactic acid is H, and it's a weak acid. Now, how do we know it's a weak acid?
Because it's not one of the 6 strongs.
So I'm going to just dissociate. It's just got one hydrogen coming off. We'll learn about that other thing in just a few minutes.
So all those other hydrogens aren't acidic hydrogens?
No. Yeah, the only hydrogen that breaks off is this first one.
Yeah.
And this right here is the lactate ion.
Yeah, so don't try to make it have 6.
Yeah, that's a good point. So we have an ice table, but we're trying to find the Ka. Now we know the Ka expression would be the concentration of the hydrogen. It's going to work backwards. Times the concentration of the lactate, C3H5O3 negative, over the C3H5O3.
Yes.
So if I knew each of these values right here, the hydrogen value, the lactate value, and the lactic acid value, I would just simply plug them in.
And we do know some of them. We're given the lactic acid value. It's 0.100 molar.
Well, not exactly. We know it's 0.1. What is it?
0.100 molar. It's in the initial.
Initially.
Yes, in the initial.
And this value here is 0 and 0. Now, we've normally said minus x and plus x,
right.
But we have this 3.7% number. Now, 3.7%, if you recall, was the x after you do the math. So if I took 3.7% of the 0.1, that would be the value of the hydrogen ending value, which is 0.0037. Now, how did you get that number, Mr. Sams?
I just figured out what 3.7% of 0.1
So you took 0.037 times 0.1.
Right.
Now that's equal to the hydrogen value. That would also be equal, by the way, folks, to the lactate
ion
0.037. Now why is it that? Because if you look in the balanced equation, this is a 1-to-1. So they would be equal. Now, this would then see plus 0.0037. This would be plus 0.0037. This would be minus 0.00.
Because it's also a 1-to-1 ratio there.
This ratio here is 1-to-1. By the way, if it's a 2, then we have to put a 2 or whatever.
Right, so just double it.
So 0.1 minus 0.0037 is 0.0963. So now I plug my numbers in. 0.0037, that's the hydrogen value, times 0.0037, you could just square that, divided by 0.0963 gives you your Ka.
1.4 times 10 to the negative 4. I'm going to look that up and see if we got it right.
Yeah, I don't know if I made this problem up or if, we could lie and say it's a different temperature or something.
Yeah, I actually don't have that one listed, so
I
won't be able to look it up. We're going to trust our math.
I think we're probably right. Hey, we now have some acids that are a little different.
Polyprotic. Poly means more than one.
Poly means more, yeah.
Many.
So more than one. And so some acids have more than one hydrogen. So if you look at phosphoric acid, it has 3 hydrogens. And carbonic acid has 2. Most of the acids we've done in the past are HA, etc. So let's kind of talk ourselves through this. There are 3 different varieties of acids. There are monoprotic acids. Monoprotic acids are just HA.
And those all have an anion with a -1 charge.
Yeah, so A has a -1 charge in this case, and that would just simply break apart into H's and A negatives.
Yep.
Now, diprotic acids,
2 protons.
that means they have 2 protons or hydrogen ions. So that formula, and then therefore for this to work, the A must have a charge of
-2.
-2. All right. Now that means therefore the formula of a diprotic acid is H2A. Now I need to write the dissociation of this a little differently than we've seen in the past. It's going to break apart into H's and HA negative. This is a first step. Actually, when these break apart, they break apart
in stages.
In stages.
Yeah.
So the first stage or the first step is H2A, and then the HA negative can break apart into H's and A2 negatives.
And if you look back on your table, you notice that each of the dissociations has its own K value.
So they have a Ka1 and a Ka2.
And Ka1 will always be bigger than Ka2.
Yes.
And Ka2 will always be bigger than Ka3.
Actually, you're jumping ahead, but that's very good.
Oh, hey, look at that.
Ka1 is greater than Ka2. And Ka3, if there's a third one, is less than Ka3. Usually the jump between A1 and A2 is huge. And A2 to A3 is not as huge, but it's still
big.
Still big. Okay, so where was that? Oh, right. No, I want this screen.
Oh, yeah.
So therefore, when we write the Ka expression, the Ka1 would be equal to the concentration of the hydrogen times the concentration of the HA negative over the concentration of the H2A. And the Ka2 value, and you could look that up at whatever chemical it is, was H positive times A2 negative over HA negative. Okay? Now, for a triprotic acid, this of course would have
3 protons,
3 hydrogens. That means that the A has a charge of -3, so it's H3A. Now those reactions, this is a bit tedious, I know, H3A would dissociate stepwise into hydrogens plus H2A's negatives. And then this H2A negative would break apart into hydrogens plus HA2 negative. And then the HA2 negative would dissociate into hydrogens and A3 negative. And you can write the expressions. I don't think it's important that we do that. You'll see, because we'll do it on the problem.
Yeah.
We have the uber long
problem. We
have
the polyprotic acid problem.
It's not the longest problem of the year. That happens in chapter 15, which is next chapter, so we'll get there.
So this is the second longest problem of the year.
Yeah, it's pretty long. I don't know if that's, well, we'll see. All right. Calculate the pH and concentration of all species in a 3-molar solution of phosphoric
And by
acid.
species, we mean any sort of ions that's in solution.
Yeah, this is going to be a lot. So this is a very long problem, because this is a what protic acid, Mr.? This is a triprotic acid.
Did your tablet just die?
I'm trying to figure that out.
Maybe your battery died. Should we plug you in?
I think we should
Let's
be
hit
plugged
pause and
in.
plug you in.
So this is a very long problem. Okay, so now we're going to have to do this one step at a time. I'm sorry, this is long, ladies and gentlemen, but it just is. So if I have H3PO4, the first step is he's going to break apart into H's and what?
H2PO4 minus.
And we have to do an ice table ball game here. Our molarity was 3?
3 molar.
So this is a 3.0, 0, and 0. It's a weak acid.
Yep.
So we'll say minus X.
Here's your Ka values, Mr.
3
Bergman.
minus X, 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 X. So my Ka1 is equal to 7.5 times 10 to the minus 3. Just look on the chart. Okay, and that would be equal to X squared over 3 minus X. X is equal to the concentration of the hydrogen, which is also the concentration, by the way, of the H2PO4 minus, right? And that is equal to, from your solver, you just do the whole solver ball game.
Yes, 0.146, or I don't know how many sig figs we need here. We need 2 sig figs, so 0.15.
All right, 0.15. So that is the molarity of these two species. Now, but the problem is that we now have H2PO4, and that participates in the next reaction, as
Yes,
does the hydrogen.
and so does the hydrogen, yeah.
So now I take my H2PO4, this one right here, and I write a dissociation of that. So then I take the H2PO4 negative, and he dissociates into hydrogens plus HPO4 negative 2. My initial concentration of this is, ICE here, is 0.15.
We got that from the last problem.
So if you look back at the last problem, the H2PO4 was 0.15. But the hydrogen was also 0.15, so I'm going to put 0.15 in for the hydrogens. Now this number is 0. So this will be minus x plus x plus x. So now instead of it being like an x squared problem, it'll be a little different. 0.15 minus x, 0.15 plus x, and x. So now I find the Ka2 value from my table guy, and that is 6.2 times 10 to the minus 8th. And that will be equal to 0.15 plus x times x over 0.15 minus x. And then when you put that into your solver, actually I think I know the answer already.
Oh, do you?
X will be equal to 6.2 times 10 to the minus 8th moles per liter.
Okay.
Now how do I know that?
I'm looking.
X is extremely small. So I take the 0.15 plus the x and the 0.15 minus the x. They're going to be pretty close to 0.15.
Oh, yeah.
And then the 0.15s cancel.
Kinda cancel
If you want to
out.
put it in your
You're
solver,
right.
trust me, you're going to get 6.2 times 10 to the minus 8.
You're
It's
right.
probably 6.1999 times 10 to the minus 8.
Yep.
But from a sig fig perspective, this is x.
And that's good because that's going to have you hit pause so I can put it in the solver because I have to use a
And
different format than this one.
X will be equal to the concentration of the hydrogen.
Not the hydrogen.
It is, sort of.
Well, yeah.
No, that's equal just to the concentration of the
HPO4.
PO4 negative 2. The concentration of the hydrogen
Still basically 0.15.
is 0.15 plus x, which is what?
0.15. Because x is tiny,
Uber
tiny,
small.
tiny.
Okay, so, all right, so let's keep going, and we'll summarize in a little bit.
Yep.
Now I take my HPO4 negative 2, and I dissociate that one more time. Oh, my word, are we ever done? PO4 negative 3, and this was 6.2
times 10 to the negative 8.
times 10 to the negative 8th. This is
0.15.
0.15, and that is 0. We say minus x plus x plus x. 6.2 times 10 to the minus 8 minus x. 0.15 plus x, x. Now we knew our Ka3, which is an
4.8
4.8
times 10 to the negative 13.
very tiny,
Bitty bitty.
equals 0.15 plus x times x over 6.2 times 10 to the minus 8 minus x. Now, I think you should put this in your solver, Mr. Sanders.
Okay. I'm going to hit pause. It's going to take me a second.
Well, so x is equal to 1.98 times 10 to the minus 19th. And actually, Mr. Sams did not use his solver to solve that because he is amazing. Actually, no. I mean, he is. But but x is now uber small. So actually, if you think about it, if the plus x and the minus x are so small, you could almost kind of pretend this is 0.15 and this is this, and then you just have x over 6.2, and then you just solve for x, and it becomes a very, very tiny number. And that is equal to the concentration of simply the phosphate. So let's summarize our answers. All right, because now what do we need to know? All species. First of all, have the H3PO4. And the H3PO4 we found was 3 minus x.
And the x in that one was 0.15.
The x from the first one was 3 minus 0.15.
So 2.85.
2.85 molar. So after all is said and done, it is a 2.85 molar solution. The second chemical that we had was the H2PO4 minus, and that was equal to
0.15.
0.15, because that was x, if you will.
The first one.
Then we had the HPO4 negative 2. You can look back. We had to jump screens.
Yeah.
This is going to be the 6.2.
Yeah, times 10 to the
There's
negative 8. No,
X
yeah, you're right.
Times 10 to the minus 8th molar. And then we just got the phosphate concentration. And that was small, 10 to the minus 19.
10 to the minus 19, yeah. I don't
I'll
remember
look at it.
what
What was it? 1.98, or let's say 2.0 times 10 to the minus 19th molar. Very, very low.
And hydrogen ions.
And we have one more left, and that is the hydrogen ion, and that, of course, is just going to be
0.15.
0.15. Actually, plus this number, and then plus this number.
Which is
0.15.
0.15.
Equal to 0.15 plus these two equals 0.15 molar. And if I wanted to find the pH,
which we do.
And the pH, of course, is the negative log of 0.15, and that would be 0.82.
And that's an acidic pH, and this is an acid, so it makes sense.
Sorry that's long, but that's how polyproducts work.
Yay.
Hey. Okay. Now, are all acids acids?
Huh?
I mean, no, I'd say that. Are all chemicals, if an acid's an acid, it has to be an acid. Are there other chemicals that are acids?
There's other things that have acidic properties, yes.
Yeah, and so hence the screen that you're looking at, we have salts that are acids. What's a salt?
Salt is any ionic compound.
So first of all, folks, you got to understand, when we use the word salt, do not think of what you sprinkle on your French fries. Salts are ionic compounds.
Yeah, we were talking about bacon earlier. You know, that salty flavor in bacon is not from sodium chloride. It's from nitrates or nitrites, or one of those in there.
I didn't know that.
And a bunch of other stuff. That kind of gives it that weird bacony flavor, too.
I didn't know that.
Yeah, it's got all sorts of fun
So
stuff.
ionic, what's that mean, an ionic compound?
Metal and non-metal.
So you have a metal bonded to a non-metal. So, but some salts are acidic or basic.
Yep.
So when you think of an acid, you think of HA. Or whatever. And you think of base, you think of, XOH or something. Or possibly something with that nitrogen, like NH3 or whatever. But guess what? There are chemicals that are acidic and basic that are ionic compounds or salts. And that's what we want to kind of get at here today. Okay, so this is just a big conceptual thing to understand.
Yep.
All right. Let's come back to this, I think. So let's kind of give some examples of some salts.
Yeah, salts of weak acids.
So if I have a weak acid, so can you give me a weak acid, Mr. Smith?
Acetic acid.
So acetic acid is HC2H3O2. So the salt of a weak acid would actually take the anion of the weak acid, not the hydrogen, because the hydrogen here, of course, is the chemical responsible for acids. Okay, so acetic acid, the salt of the weak acid, would be something bonded to acetate.
Yeah, like sodium acetate.
So if I have sodium acetate, NaC2H3O2, this is not a pH of 7.
No.
It's actually a base, yes.
Yeah.
Now, how do we do this? What we do is we essentially kind of ignore the sort of the naklonosos that we talked about a long time ago. We ignore the sodiums and such like that, because if we take the acetate ion, C2H3O2 negative, and we react it with water, when in doubt, react with water, what happens is this creates an equilibrium system, and the hydrogen jumps and makes acetic acid.
Right.
Now, when it does this, though, something amazing happens, of course, is it leaves your OH. So we say plus OH negative, and of course OH negative is...
It's basic. Anything with free hydroxides floating around is a basic system.
So if I had some sodium acetate, and I dropped it into a beaker filled with water, sodium acetate's a solid, and we did this like in an all-day lab. We put some sodium acetate when we made our buffer. We take that sodium acetate, and as it dissolves, it undergoes this reaction, and it produces hydroxide. If you stuck in a pH meter of some variety, you would discover that the pH would be what?
Greater than 7.
It would be greater than 7. It would be a pH greater than 7 because of the production of this hydroxide ion.
And we can actually calculate what it'll be. We'll do that on the next podcast.
Yeah.
But for now, let's just deal with concepts.
Conceptually, yeah. Now, this is very, 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 very important that I want you to think about these two. You see, this acetate ion is kind of partnered with the acetic acid. They're partners in my mind.
Yes, conjugate acid-base pairs.
You see, because this really is the acid, if you recall, from a long time ago, and this is his conjugate base. So if you have a weak acid, his partner, which will be the anion, the negatively charged part of him, will always be a base.
Yep.
And the opposite is true. We'll talk about that in a second, too. The weak base, his partner, his conjugate acid, will always be a acid. And what is the difference between the conjugate base and the acid? What's the only difference?
Presence of the hydrogen ion.
You see, the only difference is this one has the hydrogen, and this one does not. So the one with the hydrogen, the one with more hydrogens will always be the
Acidic.
acid. The one with the less hydrogens will be the base.
Yep.
Not these hydrogens.
No.
It's the missing hydrogen here that makes this a base. And makes it a pH greater than 7. Okay, this equation is huge to understand how to do that.
Yeah.
Let's summarize it just with a symbol. So if you have the weak acid HA, his partner, I call it a partner, and that's not really a true chemical term, but it seems to make sense for a lot of people, is A negative. HA is an acid, A negative is a base.
Yep.
And another thing to important note, whenever we're writing reactions, I want to say this: partners always appear on opposite sides of a reaction. You would never, for example, write C2H3O2 negative plus HC2H3O2 like some kind of arrow thing. Never, ever, ever, never, ever, ever, never, ever, never, then if never, do this.
So.
Because this will create, a lot of students will do this, and it messes all of your math up.
Yep.
Nasty, nasty. Okay.
So we can do the same thing with bases. Oh, no. We didn't have a base slide.
Yeah, let's do a base slide. We need to talk about bases.
We do.
So let's say, so add this to your notes, ladies and gentlemen. If I have ammonia, his partner would be
ammonium.
And what's the difference between the partners?
A hydrogen ion.
You see, the difference is that the old H positive is, if you were to take this H positive, it can turn, right here like that, right? One hydrogen. So if I have ammonium chloride,
okay,
the ammonium,
and we put it in water,
plus water, will make this hydrogen is going to jump on board with the water and make hydronium, which is the acid piece, plus ammonia. Notice that the partners, ammonia and ammonium, appear on opposite sides. You must have opposite sides or you would do problems. You will create, or you will be wrong, and wrong is bad. So, you don't want to do that. Does that make sense? Hopefully it does. This is just so critical to understand. Now, notice that we wrote it with plus water. On this problem, I wrote water as H2O. On the previous example, I wrote water as HOH, because I knew this was going to be an acid. An acid, I like to write it as H2O, as opposed to HOH. Here's the one I did, the HOH, you see, because I knew it was going to be a base, and I could then see the OH negative. This is just a huge thing to understand that how this works. Okay? Well, folks, this concludes today's podcast. I think this last section will require some extra explanation from your teacher.
Yeah.
And so
this will be introduction. We'll do lots of chatting in class.
Yeah, this is just kind of to really understand this.
And later on when we talk about buffer systems, this becomes a little bit more clear as well.
Yeah, so this is just the brief introduction to it. And I'm not sure podcasts are going to work as well for this particular topic. Oh, well, have you got any more limericks?
Nah, I'm going to save it for next time. I'm kind of running out of poems.
Oh, don't have any more poems left.
No.
Okay, great. Bye.